In this section, we will talk about vectors. So what is a vector? Traditionally, a vector is a quantity that has both magnitude and direction. A vector can geometrically be represented by an arrow. In general, one doesn't need a coordinate system to represent a vector. But we want to discuss the concept of vector in the context of a Cartesian coordinate system. Suppose we have a two-dimensional Cartesian coordinate system and a point whose coordinates are a1, a2. If we connect the point with the origin, then a vector is obtained. We say the vector A has components a1, a2. So the point has coordinates a1, a2, but the vector is represented by these angular symbols. These are called angular brackets. We say a1 is the first component of the vector A, and a2 is the second component of the vector A. So in the case of point, we say they are coordinates. In the case of vector, we say these are components. In a similar fashion, if we have a three-dimensional Cartesian coordinate system and a point in space whose coordinates are a1, a2, a3, if we connect the point with the origin, a vector is obtained. So the vector has components a1, a2, a3. This is called a representation of a vector. So in general, we can think a vector and a point has a one-to-one correspondence. Whenever we have a point in space, we can construct a vector out of it. And alternatively, when you have a vector, its tip, the point has coordinates as the same as the components of the vector. Now we will talk about the magnitude or length or norm of a vector. The length of a two-dimensional vector A, whose components are a1, a2, is simply defined by this formula, which is in fact an outcome from the Pythagorean theorem. So if we have a vector A whose components are a1, a2, its magnitude is simply defined to be the positive square root of the sum of the squares of the components. For example, if a vector A has components 4 and 3, then its length A, the absolute value of A, or we can say the magnitude of A, is given by this formula, which is the positive square root of 4 squared plus 3 squared, which is simply 5. And this is shown in the accompanying figure. In a similar way, we can extend this definition in the case of three-dimensional vectors. So if we have a vector A whose components are a1, a2, a3, its magnitude is defined to be the positive square root of the sum of the squares of the components. We usually denote the length or magnitude of a vector by putting two bars in front of it. One in the beginning, the other one in the end. But in some advanced calculus texts, we also use double bars.